Now let's open up today's session with Dr. Jeremy Yates, Director of Innovation of the DiRAC HPC facility. A senior research fellow at the University College London since joining the Department of Physics and Astronomy in 2011, Dr. Yates' interests include all areas of stellar formation and evolution and the use of advanced techniques such as radiative transfer, magneto-CFD, astrochemistry, and radio interferometry. Wow, that's a bad one. In parallel to his observational and theoretical research pursuits, Yates has been a key contributor to the Science and Technology Facility Council, Research Councils UK, and its successor UK Research and Innovation, including serving as chair of both the DiRAC Project Board and the UK's National E-Infrastructure Project Directors Group, helping ensure all users, projects, and communities have access to the breadth of resources available throughout the UK. In his current role as the SDFC DiRAC Director of Innovation Technology, Dr. Yates continues to bring together familiar and disparate activities, from CPU, network, and local disk usage to job submission, data management, and visualization. Dr. Yates' expertise in workflow models, networking, and inter-campus grids, on-campus clouds has not only provided colleagues more access, he's also helping them complete tasks in a timely fashion. Dr. Yates holds a PhD in radio astronomy from the University of Manchester, and today he will present I/O solutions and problems. Thank you for joining us today, Dr. Yates. You may begin.
Okay, thank you, Brian. So the first thing to do is to apologize because you're not getting your advertised speaker. So Paul Kalaser is not able to talk. I must take some responsibility for that because, as many of you know, we are just starting a procurement for DiRAC 3, which we have to kind of get all done and dusted by the end of March next year. So we are going through various processes at the moment. I'm afraid Paul got overloaded with jobs that I had given him to do. So it is ironic and somewhat just that I've ended up having to talk. Unfortunately, Paul has not provided me with his slides, so I'm afraid what you're going to get is the last 15 minutes worth of work and thinking from me as I was having to put together our recent conversations. So I think the first thing to get across to the audience is that this topic is one that is discussed quite a lot within the UK context. It began when we were all starting to adopt parallel file systems 14, 15 years ago. Those of you who use Lustre and GPFX, which I think is exascale these days, you can all remember the kind of excitement that there was at being able to configure much more easily the I/O streams from the CPUs, the I/O communications, so that it was all going into one place rather than having to be parked in either in the servers themselves and somehow shared, or having to make use of some very, very expensive I/O technology. So that kind of progression all those years ago, the parallel file system was certainly of a huge benefit to DiRAC, and it meant that one of the first things we actually discovered, and this is to our shame, is that we discovered that a surprising number of codes that we had been assured of as being CPU bound were in fact I/O bound, and certain areas in quantum chromodynamics made rapid progress and continue to do so because they are able to make use of a high performant I/O subsystem. So this approach is now ubiquitous across the UK. You will see parallel file systems being used in many contexts. So where are we going with exascale? And two things to note with exascale, of course, is that I think Simon may have shown this on his slides. The UK definition, well, the definition that Excalibur is using for exascale is something that allows you to do 1,000 times more work than you can currently do now. And 1,000 times, of course, would apply to embarrassingly parallel or loosely coupled work. You obviously aren't going to get that kind of scaling, although we're going to try very hard to do that for actual weekly and for real parallel jobs. Of course, one of the things that's going to happen with all these jobs is that the amount of data generated is also going to go up by, between 100 and 1,000 times. And for a lot of projects, an awful lot of projects, they start moving from the gigabyte sort of low terabyte era. All of a sudden, they are moving into the large terabytes, petabytes era. Not era, but region. All of a sudden, the I/O subsystem is going to be important for them. So for a lot of people who say if you're doing AI, and AI is an obvious first port of call, as we heard yesterday, for exascale. AI relies on good data, obviously, and large amounts of it. The I/O subsystem suddenly becomes very, very important, and that's why it has to be thought about right at the beginning of the design phase. So, what Paul and I and Mark and people like Stig Telfer and John Taylor, who have been working on SKA, and people throughout the DiRAC community, so Alistair Baston at Durham in particular, what we've been thinking about is how do we demonstrate now that we can handle these kind of data loads. So the first kind of project that we thought about was, can we produce a solid state device in array form that could act as a parallel file system, and actually add that in as a faster file system in front of the parallel file system, so you could cache your stuff there, use that as your workspace, and this would be for key parts of your calculation that are particularly I/O intensive. So you may be wondering, why didn't we go out and buy it ourselves? I'm afraid we'd heard too many tales of disappointment from our colleagues around the country. So we actually set ourselves the target of doing this ourselves. And for us, it was our first major move outside of Peter Boyle's work into genuine code design. And Paul led this project and undertook it with Dell and DDN. And one of the first things we discovered is that it's actually very, very easy to put together the hardware. So that was easy. The really, really hard work was the software to actually make it work. This is a real software problem that required a lot of work with DDN, sort of on Lustre, and just to make sure that the Lustre software could work with the SSDs. This has proved to be very successful. So Paul will be showing you now his nice plot showing his people winning the IO 500, and he'll be telling you about his plans to try and win it again later on in the world in the year. It's quite important, this, because what we did was we produced one product which was for Durham. Durham typically run jobs that have about 250 terabytes of RAM. These are CFDs, they're time series CFDs. You can restart from the previous time step, obviously. What happens when that machine breaks? We get an MPI error. Of course, the whole thing goes down. So one of our design targets was to see how we could checkpoint 250 terabytes and get it down from 5 hours, which it was at the time, using a parallel file system, Lustre to 10 minutes. That was our target. And one of the first outcomes was hitting that target. I think it's actually 11 minutes, but we actually got it down to 5 hours to 10 minutes. And of course, some of the improvements we had to make in the software along the way would have actually reduced that 5 hours on the parallel file system as well. What that means, of course, is that the Durham system is now, rather than spending 5 hours a day checkpointing, it's spending about 10 minutes a day checkpointing. That's a big productivity boon for us. I'm sure you can all work it out. That really is. It's like getting another 25% of the system back, right? Because everything was just sitting there idle while some poor node was just dumping stuff via DDN, via a parallel, via Lustre into the parallel file system. So that was the second one, and so a nice, very simple problem, and we always believe in doing nice, very simple problems first. So, of course, it's not random, of course, it's a nice string, right? And what the next thing that we uncovered, which was with is actually using the same disk array, SSD array, in order to kind of use it as a regular file system. And that's when we discovered that the parallel file system and some of the deeper BIOS type settings and some of the firmware needed to be looked at again in order to allow it to actually act as a regular parallel file system. If Paul were here, he could tell you what they are and what they have to do. And one of the things that has come out of this is now that we have a SSD array that can now do this, can actually function as a regular parallel file system. It's very, very fast. I have to say that it's very, very fast, and we're rather glad that we've got it ready for DiRAC 3 as a very important piece of technology, because DiRAC 3, some projects are going to see 7-8 times uplift in the data that they produce, and having this large SSD of around a petabyte, the SSD array of a petabyte, means that they can that they'll be able to kind of do their I/O, even though there's 7-8 times more of it, in the same kind of time that they're doing at the moment. So this is one of the reasons why Paul and John called call this data acceleration, because it's actually, as well as accelerating the kind of data flow, it actually acts as an accelerator of your work. So these are kind of very simple-minded examples. We kind of now know this, they're simple-minded. It seemed very complicated at the time. But one of the things that we've now been musing on is, okay, we've now got it up to, where you've got 100,000 calls, you can deal with the large I/O, because being lattice QCD and astrophysics, we do generate very, very large data sets. So if we have a look at, I hope you can see the next slide, the kind of big data challenges that are coming down the line for us. We've been talking about exascale, but of course, one of the X's is already here. So exabyte is already here. And we have one project, of course, which the UK is heavily involved in, which is CERN, which is the Large Hadron Collider, and the Large Hadron Collider compute grid. And we have our local instantiation of that, which is the very successful Grid PP project. That's already at the exabyte level, and it's already shifting in an automatic way around 5 to 10 petabytes a week from CERN to the UK. And we just had our link upgraded, so it'll probably be even more. So think about that. All that data is flowing out from CERN along what's often jokingly called the World Wide WAN, or is it a big LAN? There's a bit of an argument over what it is, but in effect, it's a very, very large worldwide area network. And one of the things that they've been doing for a while and not really telling anyone is that they've actually been using the network, which in our case is called Janet, as a way to super cache, both storing data in effect in the network, as well as making sure that it ends up at the right Grid PP site at the right time for it to be reduced. So some of these ideas from high throughput computing, we're now starting to see are having enormous currency again in what we do, although some would say never went away, but maybe a few of us stopped doing it for a while, which is the whole thing of data caching in order to reduce job latency. And being someone who's had to set up the Excalibur hardware-enabled software program, along with Simon McIntosh-Smith, but also someone who's very, very involved in the DiRAC-3 procurement. One of the things I'm really getting a sense of from the technology providers, so the vendor community, are various ways of how you reduce the I/O contribution to job latency. And it's nice to see data caching coming back and being made an explicit part of this. And so again, it's seeing this crossover between traditional HTC and traditional HPC, the same concepts. I mean, the latencies might be different, but it is the same concepts. And actually in a unit time, there's a very large amount of data being shifted. One of the UK's great focus, and of course I am a radio interferometrist, have been for 30 years. Ooh, it is 30 years as well. It's one of my most active fields. One of my largest collaborations I belong to is interferometric measurements of flows from stars, which is actually tied to a very active modeling program as well to interpret the data. square kilometre array is the next big thing. John Taylor and Stig and Paul have worked very heavily on this as part of the Science Data Processor specification. They now have to turn all of that into real stuff down in Australia. And it's the huge data rates at all stages, from the telescope to the Ska Data Center. So the Ska Data Center is this kind of set of data centers in the UK and across the world, which are taking the data products. So the SKA is in a sense one of the first great tests of exascale I/O, which is what's really prompting certainly my interest, because if you're a stellar astronomer, radio is not a good wavelength to observe stars, even though it's the one that will give you the best resolution. And so we have been waiting for SKA all my career, so that's 30 years. I remember seeing SKA posters 31 years ago, and it's taken that long. It's a big problem. There's a lot of data that has to be collected and then processed. It also has to be filtered for imperfections that are inserted by the atmosphere or by satellites or various interference, but also the actual response of the instruments themselves and the wires that they travel through. It's a beautiful AI problem, absolutely beautiful, and that is actually part of AI is going to make a huge contribution to this. So in UK terms, this is going to be an enormous driver of the development and deployment of I/O subsystems that can operate at exascale data rates, and indeed at exascale data volumes as well. So things like the SSDs and the DAC arrays, the data accelerators, are going to play a key part in that. One of the things that they've had to deal with is use of cloud technologies. An awful lot of work has actually gone into making cloud operating systems, so in this case OpenStack, so scientific OpenStack, be able to kind of handle these huge data rates, and that's been a very successful project, I think. But the last thing that they had to deal with are issues around security and things like that. All these little bits of software that have been written over the years to protect us now start to get in the way, and it's having to deal with those things that act as choke points at the data rates that we want to function at, and yet keep the actual good sense that was in them. So it is actually quite an important thing. So over the next few years, we're going to move from data producing things to things that produce their own data, which of course is simulation and its sibling AI. There's a lot of talk yesterday about AI taking its place within simulation through emulators. So I have a PhD student working on emulators or surrogate models. I'm offering MSCs in that as well. 3 years ago, I would not be saying that. Now it's a fairly big chunk of what I want to do next. So for me, this is actually a key thing that we need to understand, particularly the I/O. So remember, you've got this AI trying to learn from something. Where is that something, and how is it going to be, and how is it going to be accessed and updated, right? So you've got these large data structures somewhere in your system. Where are they? What are they linked to? And those are very key questions now. So this is the I/O subsystem is now really important. So that's why the UK is focusing on it in particularly at this time. So the current areas of study, so we're looking at data rates, we're looking at the extension of the hierarchical storage model to include NVMe, data accelerators, of course, better parallel file systems, and integrating tape and cold disk. So it's all a continuum, it's all a unity from our perspective. Looking at local pools of storage in the cluster, so you would have seen Simon talk about Durham doing their Gen Z project. That's really what this is about. How do we offer memory as a service? How do we offer storage as a service within within the cluster itself? Advanced caching. We have heard some great talks on that over the last 3 or 4 weeks. Reducing the job latency. As part of the need and as part of our UK Excalibur hardware and enabling software program, we're going to build we are going to build a test bed, which will be at Cambridge, which will start to look at all these various aspects. For us, one of the key learning projects, and I know Paul goes there regularly to have a look. One of the key learning projects has been the sorry, that shouldn't be that. That should be the XNS project, which I've been looking at and watching its progress for the last 3 to 4 years. Hell of a lot of an awful lot of key learning has been done. You know, it's helped us a lot. It's accelerated our understanding. It's broadened out, certainly my own understanding. And one of the reasons why I'm talking about it at the end is because I'd like to record my own thanks to the XNest project for all the work they've done in trying to understand what interconnect and what storage has to do at the exascale. It's been a really good project for teaching people like me what I might need to know. And it has kept me informed quite well. So this is not quite the talk that Paul would have given, but I hope it gives you a flavour of what we want to do. We are doing a third design of the SSD arrays over the next 2 months. It's obviously because we want to get the kind of new prototype, which will be a lot more powerful than the current SSD that we have, ready for DiRAC 3, which will be deployed in Q1 of next year. So, and also that will then serve as a prototype for the Science Data Processor. Okay, which is because I think you can all appreciate why having large SSD arrays for the data for the SKA is actually a key part of that system. Okay, thank you for your attention.